Welcome to Lecture 3.5, Damped and Forced Harmonic Motion. In this lecture, we will extend what we did in the previous lecture from just simple harmonic motion to cases when we have damping and forcing terms. We're not going to do it in the full generality when we have damping and forcing as much as possible. That's more of a topic for an engineering course, but we will do damping and we will do forcing, and we'll see a neat application of this as well. Okay, so recall from last time that if x of t is the displacement of a mass, let's call it m on a spring, then x of t satisfies the following second order linear differential equation where c is the damping constant, omega naught is the frequency, and f of t is the external driving force. And in the last lecture we assumed that this was 0 and this is 0. Although I guess in one case when we had gravity, that would have been an external force. So in this lecture we will analyze the cases when c is non-zero and when we'll do a specific example when f of t is sinusoidal. Okay, so let's start with the case when we have damping, but let's assume there's no driving force. And that means that the right-hand side of this equation is going to be 0. Mathematically that means the equation is homogeneous. So let's divide through by the mass m to make this term monic, and we get a second order constant coefficient ODE, like this. Technically I probably should have kept the m under here. I was thinking to divide through by this and just re-Christian these constants like this, but I think a better way to say this is not divide through by the mass m. It's probably by saying assume that we have unit mass. Assume that m is 1. Let's do that. That'll just make things easier. Okay, so in this case, this is a constant coefficient homogeneous ODE. We know how to solve it. So we guess that there is a solution, x of t, which is e to the RT. If we do this, we plug it back in, we'll get a characteristic equation, which is r squared plus 2cr plus omega naught squared is 0. And so we can solve for r using the quadratic equation. So this gives us r equals negative b, that's negative 2c, plus or minus b squared, that's 4c, minus 4a, and again the c is part of my b. Yeah, sorry about that. No way to really avoid it. B squared, which is 4 times c squared, times or minus 4ac. A is 1, c is this, so that's minus 4a times omega naught squared all over 2a. So that's all over 2. So we can pull out this 4. It's actually a root 4 to the square root, and then we get 2's everywhere, and then we can cancel those. And so this is just equal to, so r equals negative c plus or minus c squared minus omega naught squared. So that is why we chose to put a 2 here. We didn't have to. It made things easier. It made this simpler. Because we want to analyze what the solutions are for this, and we already know that it depends critically on what type of roots we have for this, whether these are real, whether they're complex, or whether we have a repeated root. So let's actually write this down. So we have 3 cases. So the first case is when we have complex roots. So complex So when this equation, or when these are complex, that happens, notice that happens precisely when c is less than omega naught. So when this under the square root is less than 0, that happens when c is less than omega naught. And in this case, we say that our system is underdamped. And in that case, our solution is x of t is e to the negative ct times a cosine of omega naught t plus b sine of omega naught t. And this is all stuff that we've seen before. This is our a plus or minus bi. Refer to a few lectures before for why this is the case. Okay, so case 2 is when we have a double root. That happens precisely when this term is under the square root is 0. So that happens when c is equal to omega naught. So when we have a double root, happens when c equals omega naught. This is said to be critically damped. So our simple harmonic, or our mass spring system, that is. So you should think of it like a mass oscillating with damping. So it's going to oscillate back and forth, and then it's going to slow down, and finally peter out. So when it's critically damped, the solution to this differential equation, this is also something we've done, is x of t is equal to c1 e to the rt. In that case, r is actually equal to negative c. All right, when this is 0. So let me actually write that down. Turn that into a negative ct plus c2 e to the actually c2t e to the negative ct. Remember that when we have a double root, then we still have one solution of this form, and the second solution is the same thing, but it has a t in front. And finally, the last case is said to be overdamped. So this is when we have two real roots. That happens when c is greater than omega naught. In other words, that happens when this is a positive number under the square root, and that is said to be overdamped. So in this case, x of t is c1e. Let's suppose the roots are r1 and r2, e to the r1t plus c2 e to the r2t. Notice that these roots are always going to be negative numbers. So note that r1 and r2 are going to be negative. So these things are actually, these aren't growing, these are actually dying exponentials, because whatever the heck this is under the square root, it's less than c squared. So this term, including the square root, is going to be less than, in absolute value, less than c. So we have negative c plus or minus something smaller than c. So both of these are going to be negative. So if you actually were to plot these three graphs, or these three equations, of course it depends on a, b, the actual values. But let me give you a general idea as to what's going to happen. I'll plot. I think I can fit all three of these here. So for these, let's plot t and x of t. So when it's underdamped, we have so this is a sine and cosine wave. We actually know this is a cosine wave. We can write it as a shifted cosine wave with a different amplitude. And this exponential kills it off. So this thing looks like something like this. When it's critically damped, both of these things, these are exponential functions. It's going to look something like that. And finally, when it's overdamped, this is that's when we have something that looks like this. So let me say a couple things about this. One way to think about an underdamped versus overdamped system is, well, I'm going to give you several examples, and some of you may latch on to other ones based on your experience. If you have a car, or if you have shock, well, let me draw a little cartoon car up here. So let's suppose you have a car, and you have shocks in your car. So if you push down your hood and you let go, and your shocks are overdamped, then your hood is going to slowly rise up. Whereas if your shocks are underdamped, then and you push down your hood and you let go, it's going to wiggle back and forth, and finally it's going to go back and oscillate as it goes up and slows down. This is not an example that I can latch on to, but in my experience, this is in a lot of textbooks, and when I share it in class, a lot of students can relate to this. What I can relate to is, I don't know if I could draw this one now, but let's suppose we have a screen. You have a screen door, and I'm sure you've seen doors like this, and so this is a screen door that opens and closes, and how do I want to say this? Yeah, so this is the door frame, this is the door, and you let it close. Now there's usually some little device up here, some little piston thing that you can adjust, and some screen doors, this is adjusted so when you let the screen door close, it closes very slowly. That is a damper up here that is overdamped. It closes slowly. You've also probably seen screen doors where this thing is broken or it's very weak, and when you close this screen door, it swings back into its inside and swings back and forth like this and settles off. That is a spring system that is underdamped. So what is critically damped? Critically damped is that threshold between underdamped and overdamped. Think about adjusting the shocks in your car, or adjusting this damping thing up here, and as you make it looser and looser, or stronger and stronger, there's going to be that one perfect setting that's right between when it's underdamped and it's overdamped, and that's when it's critically damped. And that is, so if you have a screen door, you actually want to adjust that damper so it is critically damped, because that would mean that your screen door closes as quickly as possible without swinging back and forth. Because the more overdamped it is, the slower this thing is going to close. And the more underdamped it is, the more it's going to swing back and forth. So you actually want to adjust your setting on your screen door, and probably on your car shocks as well, so that it is actually, in fact, critically damped. And mathematically, we have, this is the function that's sort of in between, in the threshold between, and the border between these two things. And and the t makes it different. So I'll let you think about what happens, how this behavior affects it for small values, for small values of t, and I guess just in general, how this curve differs from these two things. Okay, so our next example is when we have harmonic motion with a driving force. So in this particular example, let's consider the case when the driving force is sinusoidal, meaning it's a sine and or cosine wave. Think of this as like external vibrations or oscillations into the system. So perhaps you have a mass spring system and the spring is attached to a motor, or maybe that there's vibrations that are being exerted into whatever block the spring is hanging from. If you're an electrical engineer, you might enjoy the example or the motivating situation of the source voltage being sinusoidal. I don't know enough about electrical engineering to fully appreciate or understand this, but I've seen it in books before, and when I've shared it with students who have that background, they seem to really latch onto that sometimes. And you could also have like a structure from civil engineering, maybe a stadium or a bridge that has some natural frequency, and there's some external force or vibrations being exerted on that structure. Okay, so let's recall that C is the damping constant. Omega naught is the natural frequency of the system. Think of it like the mass spring system, the natural frequency that thing is oscillating at. And omega is going to be the driving frequency, the frequency of the external force. So in this lecture, to make things easy, we will analyze the case when C equals 0. So we're just going to assume that term is gone. And if you take a more advanced engineering class, I'm sure you'll do things where you have both damping and driving forces. But yeah, and you'll analyze things like how sensitive is the displacement to these two things, and maybe control theory type questions. For now, we're going to make things easy, and we're just going to consider the case of the driving force and how this affects the general solution. Okay, so the first case is when the natural frequency and the driving frequency are different. So recall that we first need to find the homogeneous solution. That's always first. So the solution to the homogeneous equation, that's easy. We just make this 0, and now we have a very simple second order ODE, one of the first ones that we learned how to solve. This is C1 cosine of omega naught t plus C2 sine of omega naught t. Okay, so next we need to find a particular solution. And we also know how to do that. We learned about the method of undetermined coefficients. We learned that we need to guess or assume there's a solution of the form of the forcing term. So in that case, it can't just be cosine omega t. It has to have a cosine and a sine in that. Recall that. So we are going to guess that that there is a particular solution of the form a cosine of omega t plus b sine of omega t. And we need to solve or find both a and b. So we need to find a and b. And then we're done. We just add that to our homogeneous solution. So let's plug this back in. Plug back in. So plug back into the differential equation. So let's do that. xp double prime plus omega naught squared xp. So I'm actually going to let you compute the derivative in your head. Not two derivatives, because when you take two derivatives, you're going to get the same thing back out, but you get omega squared. It pulls out, and the sign, sign flips. So this is going to be, let's see, so this first one is going to be negative omega squared times a cosine of omega t plus b sine of omega t. And then we have to add, I'm not sure I'm going to have room for this, we have to add omega squared, omega naught squared, times, times this thing, this is my xp, so a cosine of omega t plus b sine of omega t. So before we set that equal to the right-hand side, let's collect terms a little bit. This is going to be equal to, okay, so we have some number of cosine of omega t plus some number of sine of omega t, and we have to set that equal to the right-hand side, which is, let's see, how do I want to, which is a cosine of omega t plus 0 sine of omega t. Let's underline those just to emphasize. Okay, so how many cosines do we have? On the left-hand side, which is right here, we have, let's see, we have negative omega squared times a plus omega naught squared times a. So let's factor out a there. So let's write that as a, and then omega naught squared minus omega squared. That's how many cosines we have. So from this term and this term. How many sines do we have here? We have negative omega squared b plus positive omega naught squared times b. So that's going to be plus b times omega naught squared minus omega squared. So now we got a system of equations. We have to set this thing equal to a, and we have to set this thing equal to b. So let's do that. So we have a times omega naught squared minus omega squared equals capital A, and we have b times omega naught squared minus omega squared equals 0. So this is a system of equations. Well, we know that omega, remember, by assumption, these things are different, so this is non-zero. Omega squared and omega naught squared are non-zero. These are both positive numbers. So that means b. So that means b must be equal to 0. So we get that b equals 0, and we can solve for a, and we can solve for lowercase a, and a equals capital A. So we're just solving for lowercase a up here over omega naught squared minus omega squared. Okay, so now we have a particular solution. Remember, our particular solution was this, and now we know what a and b are. So let's write it like this. Xp of t is big A over omega naught squared minus omega squared times cosine of omega t. So now our general solution, let's write it in this big empty space. Our general solution is our homogeneous solution plus our particular solution. So that's going to be C1 cosine of omega naught t plus C2 sine of omega naught t plus capital A, that's the amplitude of the forcing term, divided by omega naught squared minus omega squared times cosine of omega t. I notice that this omega is different. This is the driving frequency, and these things are the natural frequency. So let's box that right here. Okay, and next let's ask ourselves, well, what does this solution look like? I mean, we know we can plot this, but we don't really understand what it's like to add a cosine wave of this cosine. Well, we know this thing here is a cosine wave. a shifted cosine wave or shifted sine wave of a different amplitude. But we don't know what it's like to add that thing to this cosine wave because the frequencies are different. Okay, so thus far we have a second order differential equation that represents harmonic motion with a driving frequency that's sinusoidal, where the natural frequency of the system and the external frequency are different. In that case, our general solution looks something like this, and this looks complicated, but think of these two terms as just being a simple shifted cosine wave with frequency omega. Remember from a couple lectures ago that we can always write this as a single cosine wave. And this is just a number, and this is a cosine wave with a different frequency, frequency omega. So you can sort of think of this as two sound waves, this cosine wave and that cosine wave, with little different frequencies. So we want to understand what this solution looks like. It's not clear what we get when we add these things together. And I'm not going to prove this, but I'm going to appeal to your intuition that it shouldn't make too much difference what the initial conditions are in terms of the long-term behavior of the system. So let me sketch this. So let's suppose we have a mass spring system, so something like this, and it's at equilibrium. And let's suppose that we exert some vibrations to the system right here. So maybe there's some sort of vibrations that are going back and forth. You can think of that. Maybe it's not as natural as jumping up and down and stomping your feet on this, if this is like the ceiling. But let's think of this as like there being a motor on here, and this motor is going up and down like so. So when you apply f of t is just this driving term, then this motor goes up and down like this. So what we're going to do is, this is a general solution. I'm going to make up some initial conditions, and I'm going to solve this. I'm going to solve an initial value problem for specific values and see what we get. Then we're going to plot that. And as I said before, I'm claiming that this is not too sensitive to the initial values. Let's make the initial values simple. So let's consider equilibrium. I'll consider equilibrium. Sorry, I guess I forgot to put a little bit of. I don't have enough space there, but consider equilibrium. You can read that. So meaning we have, suppose that x of 0 equals 0, and that x prime of 0 equals 0. So in other words, the mass is hanging at position 0, so it's hanging from rest. Actually, maybe it's technically a little bit above rest, because equilibrium it would fall down a little bit, but it doesn't matter. And at time equals 0, we are not pushing it upwards or downwards, we're just letting it go. So why am I considering these initial conditions? Simply because they're easiest. They're going to make the math, they're going to make more of these constants be 0, and more things will cancel out. And again, I claim it doesn't matter too much whether or not this mass starts at 0 or -1 or -2, or whether I give it a slight push upward or downward or just let it go. At the end of the day, this system is not going to be that sensitive to initial conditions. There's a spring constant, there's a mass of a certain weight, and there's a motor going back and forth. It doesn't matter too much where I start with. The long-term behavior is going to be similar. And again, I'm just appealing to your physical intuition here. Okay, so with these initial conditions, let's see if we can do these in our head, or at least the first one. If you plug in 0, so let's plug in 0 into here. Actually, yeah, this will be easy enough. So x of 0 equals c1, all right, plus, did I do this right? Yeah, so c, that can't be, something here is wrong. Well, let's just do it. Okay, so x of 0 is C1 plus 0, because if I plug 0 into here, I get that, and then plus a over omega naught squared minus omega squared, and I get it, that's equal to 0. Okay, yeah, that's not that bad. So we get that C1 is, I want to write that as negative a over omega naught squared minus omega squared. Yeah. And next, let's take the derivative of this thing, and let's plug in 0. So x prime of t equals c1 omega naught sine of omega naught t, and I need a negative sign there, plus c2 omega naught cosine of omega naught t plus a omega over omega naught squared minus omega squared times sine of omega t, and there's going to be a negative sign out here. Turns out most of this isn't going to matter, because when I plug in 0, this term goes away because it's a sine, and this term goes away. So x prime of 0, yeah, this is why I said maybe we could do this in our head, because even though it's a little harder to do it in your head, that's supposed to be a 0. It makes it less messy and then psychologically nicer. So x prime of 0 is going to be c2 omega omega naught. That's equal to 0. Omega naught is a non-zero frequency, so that means that C2 equals 0. So with these specific initial conditions, we have a solution, x of t. Okay, so what? Let's see. So we have said that C2 is 0. We know what C1 is, and C1 is just that is 0, and C1 is the negative of this thing up here, right? It's just the negative of that. So x of t is a over omega naught squared minus omega squared times cosine of omega t minus cosine of omega naught t. Let me box this. Okay, so let's say a couple of things about this. So this is a number. This number is, so a is the fixed amplitude of this guy. And this thing at the bottom, this gets smaller and smaller as omega naught and omega get closer together. So as omega and omega naught get closer together, this fraction grows and grows. And this is not going to be defined when omega naught and omega are actually equal to each other. So again, the closer these two frequencies are, the bigger the amplitude of whatever this thing is. And it turns out that this is a superposition of waves with different frequencies. So if I want to ask if you could ever experience this in real life. If you've played music, you probably have. If you've ever heard two musical notes being played together that are slightly off tune, like suppose you have two trumpets in a band and they're trying to play a middle C and one of them is a little bit flat, then you hear sort of a pulsing sound. It's like sort of like that. And then the closer and closer those notes get together, the slower those beats are. So if those notes are really close together but out of tune, it's and then when they're further apart, it's but the beats are weaker magnitude. So if your notes are a half a step or a whole note out of tune, you're not going to hear this phenomenon. It's only when they're a fraction of a step out of tune that you're going to hear this. So maybe another example is if you've ever tried to tune a stringed instrument, like a guitar, you will maybe tune one string to an app online or an actual tuner, and then you'll tune the other strings off of that. So in that process, you probably will pluck two strings at one time, and you've surely had the experience of plucking two strings that are not quite in tune, and you hear this beat phenomenon. So what this looks like, let's write that down. So this is a superposition of waves of different frequencies, and that's just what it is from looking at it. It's this wave and that wave. You add them up or subtract them, doesn't really matter. So at this point, I'm thinking of these things as sound waves. So let me plot what this thing looks like. So as an example, I encourage you to go to Wolfram Alpha or your calculator and type in x of t. Maybe at some point in the future I'll figure out how to embed these sort of things in this video. At this point I don't know how to do that. But honestly, if I were in a classroom, I would just be sketching this on the board the same way. Because I usually give lectures by Blackboard or whiteboard rather than with slides. So x of t is, so here's an example. I encourage you to do this maybe on your computer or iPad along next to me, minus cosine of 12t. So plug this thing in and see what you get. And a rough sketch of what you get, how do I want to do this? So you're going to get something like this. Now these blue lines really are not there. So these blue lines are just sort of for reference. So cosine of 11t and cosine of 12t, these things have high frequencies. So this is going to be, so what I'm drawing in the middle is I'm drawing a cosine wave with a high frequency that has this envelope between these wider sine waves, sine or cosine waves. Maybe I shouldn't have done quite so many terms like this. And of course, I'm not quite being consistent. I should be. Okay, so what is this thing that I'm drawing? This black line, this skinny thing, this is the function cosine of 11t minus cosine of 12t. It is a sine wave or a cosine wave. Turns out it'll have frequency 11.5, so it'll be like cosine of 11.5t. That's the average of 11 and 12, and its amplitude is periodic, something like this. So it's living like inside of this envelope. So how to quantify this? Let's see how to think about the best way to do this. So let's do this. So beats. These things are called beats, the things that you hear in music. That's what you call them. Let me let omega. Let's assume that omega naught is bigger than omega. It doesn't really matter. Otherwise, we can reverse the roles. And I'm going to let omega bar be the average. And I'm going to let delta. I'm going to let delta be this distance. So delta is this small distance. So I probably should write that down. Okay, so let me put a little line here to signify that I'm. There we go. So what did I say? I said omega bar is omega naught plus omega over 2. And let's say that omega minus omega bar, that absolute value, is equal to delta. Okay, so in this case, let me rewrite this general solution over here. So we have, x of t is a over omega naught squared minus omega squared times cosine of omega t minus cosine of omega naught t. Let me put parentheses in there. So that's, all I did there is that's supposed to be omega naught. All I did there is I copied this thing here, and now you can use trig identities. The difference of two cosines, there's a neat trig identity that allows you to write this whole thing as, actually let me give myself a little more room for, that. So this is a sine of delta t, over 2 omega bar times delta. That's just a number times sine of omega bar times t. And this is just a trig identity. So let me circle this right here. Let me say x of t is equal to this. So we can, just using a basic trig identity, rewrite this difference of cosine waves as a single sine wave with frequency omega naught, or not omega naught, it's omega bar. So in this case, this is going to have frequency 11 and a half, and the amplitude of this sine wave is actually, it's not constant. It's actually it's a function of t. So the amplitude is sinusoidal. So this is actually the amplitude. Instead of the amplitude being constant, it's a sine wave. It's a very wide sine wave. It's a sine of delta t, and delta in this case is 1/2. And then the denominator is going to be 2 omega naught times delta. So take a moment at the very last thing in this slide to convince yourself why a function like this, a sine wave with a very high frequency, with an amplitude that is a very, how do I say this? A sine wave with a very high frequency that has a non-constant amplitude that is sinusoidal with a low frequency, something like this, why this function, the graph of this, indeed looks like something like this. And this is the concept of beats. And also notice that as these two things get closer and closer together, the denominator here gets larger and larger because this is a delta, and delta goes to 0, so this thing blows up. So when delta is small, this is large, and you can actually physically hear these beats because this frequency in the middle gets high, or the amplitude gets high. Whereas if delta is large, if these things are not close enough together, then the bottom of this is going to be large, and this phenomenon still holds, but this blue envelope is small enough that you really can't hear it. Okay, so the second case that we need to consider is when we have simple harmonic motion, but the frequency of the driving force is equal to the natural frequency of the system. So in this case, of course, the homogeneous solution is the same. So we have x h of t equals c1 cosine of omega naught t plus c2 sine of omega naught t. So now we need to guess a particular solution, and notice that what we want to do is assume that there's a solution of the form a cosine plus b sine. That's not going to work because that function is precisely what this is up here. That function solves a homogeneous equation. So this actually is the problem case that we talked about. This is the problem case. Let's put that in quotes, where where the particular solution, xp of t, if we were to guess a cosine of omega naught t plus b sine of omega naught t solves the homogeneous equation. So that's not going to work. So recall what we had to do to solve that is instead we have to put a t in front, so we have to guess that there's a solution. That's t times a cosine of omega naught t plus b sine of omega naught t. Actually, I should say that our example from before had the problem case where this was an exponential term, not something like this. So this is actually, so the same resolution holds pretty much for whatever, anytime the right-hand side solves the homogeneous equation. So in this case, we just take what we wanted to guess and we put a t in front. So next we need to plug this thing back into the equation. So we have to take a few derivatives. It's actually kind of messy to do that. It would take maybe 5 minutes to do. You got to do the product rule twice. It would maybe take half of the space. So I actually did it on scratch paper just a few minutes ago. So I'm going to actually write, trust me on this, what this is. So let's plug this back in. So now we have xp double prime plus omega naught squared xp. Trust me that this is indeed correct. So the second derivative of this is, it's messy. It is, so it's 2 omega naught times negative a sine of omega naught t plus b cosine of omega naught t, and then it's plus t omega naught squared, I hope I can fit this in, negative a cosine of omega naught t minus b sine of omega naught t. Both of these things being negative comes from the fact that we actually have to take the derivative twice, and so negative signs pull out. So this thing in square brackets, that's xp double prime, and then this term here is just, well, that's something that's not bad at all. That's omega naught squared times t times xp, which is, what is that? That is, I guess the t is part of the xp, so that's a cosine omega naught t plus b sine of omega naught t. Notice, I think these two terms cancel. That cancels with that. And so the left-hand side of this ODE, when we plug this in, is just this term, and we have to set it equal to, and I'll do this in red now, a cosine of omega naught t. I'm doing that in red to match the fact that this is just that. So in other words, what we have is so let's write it out like this. So we have 2 omega naught b cosine of omega naught t minus 2 omega naught a sine of omega naught t. This is simply this thing down here. So that's this number of cosines plus that number of sines, and we have to set that equal to this thing, which is a cosine of omega naught t plus 0 sine of omega naught t. So we have to set this equal to a and this equal to 0. So we got to so we need to, instead of writing the system, I'm just going to equate these, and we have to equate these things as well. So this one right here, since this is non-zero, that means a better be equal to 0. So a better be equal to 0, and then this one here, we get that 2 omega naught times b equals a. So that means that b equals a over 2 omega naught. So now we have our particular solution. So xp of t, I hope you can see that's an xp of t is equal to a over 2 omega naught times t sine of omega naught t. Omega naught t. So again, it's just this thing, but the lowercase a term goes away, and b is this thing here. So now our general solution is so the general solution is x of t is the homogeneous plus the particular solution, which is c1 cosine of omega naught t plus c2 sine of omega naught t plus our particular solution, which is a over 2 omega naught t times sine of omega naught t. So let me box that. Okay, so to summarize, we have solved this differential equation, which is simple harmonic motion with a forcing term whose driving frequency is equal to the natural frequency. This is the hitting the resonance phenomena. So the general solution is the homogeneous solution, same as we had before, but now we have this particular solution, and the thing to notice is that this is the amplitude of this sine wave, but it's not constant. It actually has a t in it. So this amplitude, let's write this down. This amplitude goes to infinity. It blows up. And that's what's going to cause the glass to shatter or the bridge to collapse. So let's do the same thing we did last time. Is let's take an example. Let's take some very simple initial conditions. How about x of 0 equals 0 and x prime of 0 equals 0. So here we're starting from equilibrium, and then that'll give us a solution where some of these terms will drop out, and with the understanding that the behavior of the system is not really that sensitive to where we're to these initial conditions, and this will make it as simple as possible. So plugging in x of 0, that's going to give us c1 plus this is 0 and that's 0 because there's a t in that. So that means that c1 equals 0, and that tells us that this term drops out, so we can ignore it henceforth. So x prime of t, let's take the derivative of this guy. So the derivative of this term is c2 omega naught times cosine of omega naught t. And then the derivative of this next term, we have to do the product rule. So we get a t over 2 omega naught times omega naught cosine omega naught t. These terms will cancel. Plus a over 2 omega naught times sine of omega naught t. Okay, so we can simplify this, but let's not, because all we're going to do is plug in 0. So x prime of 0, plug in 0, we get, let's see, we get, this becomes 1, so we get c2 omega naught. This becomes 0 because we have a t right there, so plus 0, and this becomes 0 because it's sine, so plus 0 equals 0. So omega naught is not 0, so we get that c2 is 0. So in that case, this term drops out as well. So so starting with these conditions is actually the case when is precisely when c1 and c2 are equal to 0. So that gives us just this particular solution. And if we were to plot this, this is a sine wave. So this is something we can actually plot just by inspection. This is a sine wave with frequency omega, but it's the amplitude is growing. So that, remember that envelope we drew last time? That's going to be this linear line. So that this is a t over 2 omega naught. It's that line through the origin. And so a sine wave with growing amplitude is going to look something like this. So this envelope never closes up. You can think of it as it's like dividing by 0. Compare this. So this is, let's label our axes. This is t, and this is x of t. And compare to what we had last time when we had those beats. In that case, when we had omega naught was approximately equal to omega, then we had these long beats, and our solution was something like this. So imagine as omega naught as omega naught gets closer and closer to omega, remember that what we had in the previous one. Let me actually write down what it was, if I can find it, or yeah. In the previous one, we had a sine of delta t over omega bar times just 2 omega bar times delta times sine of omega bar t. That's supposed to be a delta in there. So we had a sine wave, and as these things got closer and closer together, delta got smaller and smaller. So this amplitude got bigger and bigger. So if these things were to be equal, in this case, it's like we'd be dividing by 0 because we'd have a 0 in the bottom here. So that can't happen. So we have this, but you can think of this envelope as these get closer and closer together, as this envelope is getting bigger and bigger in its period, and in the limit, it never actually closes up, and this is what we get.